This is the May AIX Virtual User Group webinar. And I just want to welcome everybody here. I only have one thing before we get going here, and that's to talk a little bit about the IBM Systems Technical University that's in Orlando, and it's next week. So if you're going to be there and we bump into each other, make sure you introduce yourself to me and say hi. I'd love to meet you. If you still think you might get there this week, you know, management or whoever is approving your travel has just put it off, but you still might make it. The discount code for the AIX Virtual User Group people is still valid. You can see it on the AIX VUG Wiki, and you can still get a discount. So make sure you use that if you're still going. So with that, I think we'll go ahead and jump into our topic. A little bit different topic. I don't think I've really covered much of a flash or a storage related topic on these webinars yet. So we've got going to cover flash systems, all flash arrays today. And, you know, flash has really come down a lot. Memory's come down a lot, but flash systems have come down a lot. They really make performance, give performance a boost in the systems, and Power makes great use of them, especially with all the bandwidth in Power 8 systems. So it's a great new product that you can use in your data centers. And to help us today, we've got Jeff Stillwell. And Jeff is a business unit executive. Don't be too scared off by that word executive in his name. He's got some good technical experience here. He's been with IBM 9 years, helped launch the XIV product, storage product. Jeff is the executive for the tech sellers, which includes me, and also some of the architects, technical architects as well. But Jeff has both the power and the storage sellers, so he kind of has a hand in both realms, constantly talking to us about tying them together. And Jeff does a good job of that, and really knows a lot about bringing both of these together to make the best solution. So with that, Jeff, I'll hand it over to you.
Very good. Thank you, Joe. Yeah, it was fun getting ready for this presentation. As I was prepping, I've visited a number of power customers recently. And one of the things I hear continuously from power customers, especially people who've moved into the Power 8, is what an impact that has had on their workload and more importantly, on their business and getting the application performance that they're looking for. And when I've been visiting these customers and I start talking about the background that Joe just mentioned in storage, I've been covering storage for a long time. Servers as well, and at IBM as well, has been a previous incarnation. So putting the two together to me is some real synergy that can be provided. So, you know, meeting with power customers and hearing these success stories with Power 8, as I mentioned, when I mentioned Flash and that background, they all start asking questions around how those can work together. And one of the great things about having some customers who've done this is last time I was at Edge, one of our customers who had attached Flash to Power servers just told a story that blew me away. And I'll share that story with you shortly. There's a really good story about the impact that Flash had on improving his business. And when it comes to those success stories, the Flash team has actually created 2 decks. One deck has about 270 some stories, and the other deck has approaching 30 stories. These are all about Flash arrays. The larger deck, of course, goes back to our 840 when we acquired Texas Memory Systems, but comes up to the V9000, which I'll discuss the different arrays. The other smaller deck is related to the A9000, which is the product that we released most recently in storage. All of this is the highest performing flash in the industry. But the other part that I found when I was preparing for a presentation that I did in Costa Mesa for a power team was that, what was it? I think it was 77 of the stories that I found in those decks were specifically tied to power implementation. So, you know, when we start thinking about that, there's 2 things that I really want to leave you with today. And obviously having a storage presentation at a power users group, AIX users group, is maybe a little bit different. But there's 2 ideas that I want to give you today that I hope you walk away with, and a couple things that we can do to maybe prove the point if you care to follow up on this. But the 2 things that we've been doing mainly with flash storage is an application acceleration story. So I'll share a number of stories with you here about what this has actually meant from a real world case perspective. You know, I love seeing what it actually does from an application perspective. Not that it, you know, made IOPS run 10 times faster or whatever, but the question is, how much faster did batch processes run, or how much faster was the response in OLTP? The second idea that we'll get through is the workload modernization idea. So, you know, everybody I'm talking to is doing the cloud or the analytics or the cognitive, lots of machine learning that we're talking to in our space here. But the workloads that we're calling modernized workloads, you know, if I can show you a way to offload some of the hassle of figuring out the performance issues, then you'll have some time to spend on some of these other newer workloads and designing around those. And one of the things that I'll leave you with here is a concept of why flash is cheaper than disk. So all this is cool, but you know, it was funny. I've used this analogy in a few places. I love this from, I'm showing my age here a little bit maybe, but in Annie Hall, there was a scene in that movie where Woody Allen and Annie are, it's a split screen where they're both sitting with their respective analysts. And the question is, how often do you have sex? And Woody is like, oh, almost never, maybe 3 times a week. And Annie's like, oh, all the time, probably 3 times a week. So yeah, it's just a funny way of the way people look at different things. And from an application perspective, right, the question is, how often do you have performance problems? And maybe on one side of the house, the answer is hardly ever, maybe a few times a week. And on the application side, it's like, oh man, it seems like it's all the time, probably a couple times a week. So the point that I'm trying to get to with Flash here and these customers that I put up on the screen, the cool part is if you're using Flash to get that performance advantage, you know, if we can show that it's cheaper than disk, then it makes it almost a non-issue of just going ahead and moving forward with using flash storage to improve on the application performance. So let's go through this. I put a couple slides here. I left a few slides in here. There's a bunch of slides in here. I don't want to spend a lot of time on some of these, but I left them in just to give you some ideas of where we're coming from and what and maybe some ideas that you can follow up on later. There's a lot of the success stories in here later, but certainly you've all seen the power portfolio, and this is an AIX group, so a lot of, I'm sure you've covered the different levels there, from the big data and the cloud and the innovation, as well as the different sizes of machines. But what I want to talk about today then is how we can actually, as I said, add to that the benefit of those systems and the synergy of using flash storage. So I'm going to be concentrating this presentation. You know, we have a number of ways of talking about flash storage in our space. I want to focus here today on the middle 3. And the reason I'm going to focus on those 3 is because they are all based on the all-flash array that we acquired from Texas Memory Systems almost 5 years ago now. So when we looked at what flash could do, right, if you look at the history in the industry, you guys have all seen this. CPU performance is up dramatically. If we go right down the list, right, network performance is up, DRAM performance is up, everything is up except that spinning disk, right? You're never going to see a 30K RPM spinning disk. 15K is probably the best we're ever going to see, and actually, as people start looking at bigger disks, they're slowing down again. A lot of the reason for that is because of the power that it takes to actually get that 30,000 RPMs out of the spinning disk drive. So obviously, when we're meeting our business needs, we've all found clever ways to get around some of these issues. You know, one of the things that I talk to people about regularly is there's always a bottleneck in the system. Right? There's something that determines the best speed that you can get out of your configuration. And obviously, you can make that a more effective number by changing something. So it's basically back to the classic time and money, right? If you have all the money in the world, you can just eliminate all the bottlenecks. Obviously, there's still going to be some physical thing, right? 186,000 miles per second. It's not just a good idea, it's the law. You're not going to exceed the speed of light. But anyway, you know, the way people have found to kind of get around The performance, get better performance. Obviously, you can add more memory to the system and keep more in memory. And of course, we'll talk about SAP and SAP HANA before we're done here. Adding more CPUs may or may not be effective. If CPU utilization is your bottleneck, that can help. Quite often, that's not the issue. In a lot of cases that we see from a Flash perspective, when we start talking to people about what's going on with their application, a lot of times with a database and with analytics, we'll see that CPU really isn't the issue. CPUs are being utilized 10 to 15%, and wait IO is 80 to 90%. So in other cases, right, if you virtualize effectively, then maybe adding more CPUs is the right answer. The other thing we've seen routinely is people using what we call short stroking. If you can get 200 IOs out of a fiber channel drive and you need 40,000 IOs, then you do the math and you figure out you need 200 spinning disk drives. We saw a case of that not that recently now, sorry. Penn State was a customer of ours who had literally did exactly that with 200 spinning disks to get the performance they needed on the metadata on their cluster, the GPFS storage cluster. 200 spinning disks in 4 cabinets of spinning drives. We replaced that with a single 2U appliance of flash storage. So we'll talk about that example as well. And obviously the other thing that you can do is a lot of tuning and tweaking. So, what I'd like to show here is how the Flash system, there's a case that we had a couple years ago where we were going to do a benchmark or a POC with a customer. So we shipped them a flash array, 2U appliance that got there. We got there on a Wednesday. We were supposed to be there on Thursday. The customer opened up the box and it looked simple. So they put the thing in the rack, they plugged it in, turned it on, still everything okay. So they plugged in a laptop to it and started looking at the GUI, looked simple. Basically, by the end of the day, they'd configured and implemented and moved a database over to this flash array that used to be on spinning disk, and literally took the batch process from 40 hours down to 4 hours. And that was done with about 3 hours worth of effort of plugging it in, turning it on, moving the database, and running a test. So 3 hours of people time to get a 10x improvement in a batch process. Kind of better than a whole bunch of tuning and tweaking, but we'll talk about these other things that I've got on the screen right now in terms of the adjustments. I've got another chart that I want to use in a minute that addresses some of the things about software licenses and applications and so forth. So that's the setup of why we're looking at Flash. And if we look at the things that allow Flash to be extremely effective and have this impact, there's kind of 3 things that have allowed the Flash array to come into the place of being a cost-effective solution in the data center. When Flash started, of course, it was, practically as expensive as doing memory in the server. But as things, if you guys all, hopefully you're not actually picking up that little phone that's in front of you on your desk and doing that while I'm speaking with you here, but you all have one of those gizmos in front of you, and every one of them has flash memory inside of it. So that has driven down the price. And of course, as the processors, the Moore's Law, all of this has brought us to the point where we can use Flash instead of spinning disk to get better performance. And it makes it cost effective. I put this example up. Verizon Networkfleet was the customer I referred to earlier. This gentleman came in and spoke at Edge the last time I was there, and these guys are providing fleet management as a service. It was actually bought by Verizon when we worked with them. They were an independent company. But the part that was fascinating to me is, you see these numbers, 6x faster performance for fleet queries. Well, when they're providing queries as a service, they're basically a service bureau for these fleet management people. So obviously providing better response time to their customers is pretty darn important. 15x reduction in IOPS latency. I mean, really the thing that I'll talk about with the Flash system, it's not really about the number of IOPS, it's about the latency. And that's where we get the bang for the buck with the Flash system at 0.2 millisecond, 200 microsecond response time, whereas the traditional storage array is anywhere from 2 to 5 millisecond response time or higher, right? It was a nice story from a data center savings perspective of power reduction, but I'll tell you what, the thing that this guy said that blew me away is when he talked about this was the data center manager who presented at Edge. And basically his comment is, you know what, I'm not sitting here fixing performance issues anymore when we bring on a new customer. As a matter of fact, he showed us this chart. I leave it to your imagination to figure out where in this chart we actually implemented the flash array. But basically he said, when we did this, I no longer had to spend time in my data center when we're adding customers, rebalancing data or figuring out where the performance hiccup is. It just went away. So now I can spend time with my CIO going out and selling our services to other customers. So that was the thing that I really liked, is his focus on, you know, things that impact the business and being able to spend time on what actually matters to their business as opposed to spending time looking for those things that are causing performance issues or trying to figure out how to rebalance data. So, you know, the piece of this that makes our solution provide this functionality in a really effective way is the fact that we get this performance across the chart to a really high number of IOs. Now, generally, you know, we'll talk about SSDs in a minute, but generally SSD drives, actually this chart that I showed you a second ago, that was when the network fleet changed from SSD drives to our all-flash array. So when you hear good enough is good enough or SSDs and flash are the same, they're not, right? So when we do an all-flash array that's based on firmware as opposed to SSD drives that are emulating disk drives and going through traditional disk drive controllers that are 30 years old, et cetera, there's bottlenecks there that are not eliminated. So, you know, the fact that we get this flatline performance out of the array means that you have the headroom if your application does grow. Generally, we do not see anybody who needs 1 million IOPS, but they do need 0.2 millisecond response time. As a matter of fact, there's a company, online company, I won't mention their name here, but they are a customer of ours, actually a smaller customer, so, you know, don't anybody go away saying I mentioned Amazon. This is not Amazon. As a matter of fact, it was a company that had a smaller, actually they had about 8,000 IOPS when we were working with them to implement the flash array. So, you know, not 1 million IOPS, but 8,000. And at the time, the point for that application was the fact that they wanted absolute best performance from the second their customer logged into their website to the time they got their product. They wanted a superior customer experience, right? It's funny, when I look at customers or companies that I deal with, if you look at Yelp for restaurants or any of this other stuff, the comments that are really exceptional are never about the product. They're always about the service. So these guys bought a flash array to get that absolute best response time and give their customers the extreme experience. So it's about giving that performance, not about a number of IOPS conversations. So what that really look like when we start looking at how we improve the application. The Little's Law thing is what we have used for the application acceleration story. If you look at what really happens in any queuing theory, right? You walk into the supermarket, and Q over T equals R. Number of threads divided by the time it takes to run one of those threads gives you the number of results in a supermarket. You know, the number of checkers that are working divided by the time it takes to get each person through a checker gives you the number of customers per hour. In our case, what we're saying is the number of threads per application divided by the time it takes to run each of those threads gives you the number of IOPS. So when we look at this from a storage perspective and go from, you know, 5 milliseconds to 100 microseconds, the number of IOPS goes up dramatically. And what that translates into, as I mentioned a minute ago, what we've seen with a lot of applications, we have originally when we first started doing not talking about the data center modernization or the workload modernization. Everything we did originally with the Flash system was about application acceleration. So we went into a number of customers and said, look, you know, many of these were Oracle customers. And we said, look, give us the AWR report, typical report that's available in Oracle. Every shop has it. You know, give us the AWR report. And what we saw almost routinely was literally a 10 to 15% CPU utilization with a 90% weight IO utilization. So we'd run these AWR reports, and then we had a spreadsheet that did an analysis and said, if you change to Flash, just do nothing else in your environment. Don't add the number of threads, right? Changing the number of threads can be a really big deal in an application. If we do that thing as I showed you a second ago, where we just change the time it takes to run each thread, it's a very simple solution as opposed to reworking the application and doing all this. So this is kind of the result. This customer, we literally got their AWR report, and this was a customer who had big iron. They actually had some DS8s that were reaching the end of their lifespan. So we said, look, just, you know, move your single bad actor application off the DS8 and put it on this Flash. And here's what you will see from an application perspective. Your current wait time is 70%. We're going to take your wait time down to under 3%, and your application performance will be a 2x improvement. So that's what they did. They took that one application and they put it on the Flash array, and this is kind of a complicated picture that shows that they put it in the center and just took that one application, which actually resulted in another interesting thing where it was a much lower cost. Instead of upgrading to the latest, greatest DS8s, you know, maybe shot ourselves in the foot here, but it actually, to me, allowing our customers to take best advantage of their current investment, this allowed the DS8s that they had to get a bunch more headroom because they took that one application and put it on the Flash array at a much lower price point, and they were able to keep the DS8s for the rest of the stuff. But by the way, that application didn't improve by 2x like we had predicted it would based on the AWR report. Turns out they got almost a 4x improvement in the application performance. So it took us into a nice story about application performance improvement, return on investment being great because they continue to use their DS8s that they had in place. So that's kind of one of the things we see is, you know, if you're looking to where you can have the most impact in your data center, pick one application and make that change. And then there's well, we'll talk about that further. I mean, one of the things that we see is it's definitely the first hit of the cocaine. Once people start seeing that performance, it does tend to grow in the data center. So let me tell you why this is different. In terms of what we did, like I said, a lot of people are like, well, you know, SSDs are the same thing, we'll get the same performance there. You don't. And one of the reasons you don't is because we designed this from the ground up with this thing that we call FlashCore. And what FlashCore is, we actually went down to the chip level and we worked with the chip manufacturer to get APIs down to the chip level. We created these MicroLatency modules, which are 1 to 3 terabytes in capacity. So our usable capacity in array is 12 to 57 terabytes of usable capacity. But the thing here is, this is, as I said, this is not SSD drives emulating disk drives through a 30-year-old disk controller technology. This is from the ground up using FPGAs, using firmware-based management to get directly to the chips. So the only place you see disk emulation, per se, is on the front end where you define LUNs and assign them out to your host so they look exactly like they would, you know, a LUN on a power server from this looks exactly like a LUN from any other storage array with disk drives. But in the back end, there's no disk emulation with SSDs. This is all firmware-based with, it says FPGAs there. The reason FPGAs are the solution here that gives us the better advantage. Obviously, if you're going through a CPU, there's all the overhead of using an application and an OS and getting down to the hardware and then into the firmware. FPGAs are firmware-based, so there's no code in the data path here. It's all just hardware-based to get this best performance. which is why we then say, you know, when you're comparing this to an SSD, it's just completely different solution. SSDs look like disk drives. They get, you know, 1 to 2 millisecond response time as opposed to the 2.2 millisecond response time. We have code that I'll talk about the 2D RAID that we do to give you a high level of availability. But the other thing that we've done here in terms of providing that reliability is, as I said, by working with the vendor who provides the chips, we've got this level of you know, we've tied in the chips to the level that we've got APIs figuring out where the best cell is to put data, so we can do a much higher performance by spreading the data across chips, right? The interesting thing is, if you actually look at the way chips work, you know, 0.2 milliseconds is faster than chips themselves. But what we've done here with this MicroLatency module is, by working with the chip manufacturer, we can spread the data across the chip. So we're actually getting a grid of flash chips, if you will, to write the data. So we're getting better performance than the chips themselves provide by doing that grid infrastructure, which everybody who uses a power server is familiar with that whole concept of cores and so forth. This just takes that to the next step in storage, which is why we get this tremendous performance advantage. But the other thing we get is a great boost in reliability, because by using this heat management thing and knowing where chips are going bad and being able to spread data and avoid cells that are starting to wear, or just putting, you know, cold data in cells on chips that are starting to wear, we can get this tremendous performance, or I'm sorry, reliability and lifespan increase, right? You've all heard that flash chips wear out, and they do. But what we've done is, by doing this heat binning and being able to put data in the right place and tracking the chips down to the cell level, we are able to, ready, willing, and able, we put a 7-year guarantee on this array for the reliability of the data and the chips. So these chips are guaranteed to last at least 7 years. That's actually an interesting point as well, in terms of, you know, the cost factors and how long you can actually use this technology. So we take those micro latency modules. We did a couple things on those modules. We spread the data across multiple sets with multiple FPGAs, and we do this thing called variable stripe RAID, which we'll talk about in a minute. But then we take 12 of those modules and we put them in this array, and we do a RAID protection that allows us to have no single point of failure. So this is indeed an enterprise class storage array that is based on flash chips from the ground up. And that's how we get the performance and we get the reliability with no single point of failure. This is enterprise class flash storage. Now, this is called the FS900, and it is indeed the goes fastest in the industry as well. This is the gizmo that at the back end is 0.1 millisecond. I've said 0.2 millisecond in most of the comments that I've made this morning, because that's what you see at the application layer. So this is the goes fastest, and it's the IndyCar, which we'll talk about again in a minute as well. But what I mentioned is there's this idea of variable stripe RAID. So we actually take that level of integration that we did with the chips, and we do this thing called 15 plus 1, or a 15 chip, a 14 plus 1 stripe set. But we actually do 16 of those across those chips. So we do it at the page level in the chip itself. So now, if we actually have a piece of a cell that goes bad, we can change that one stripe set to a 13 plus 1. So that's the variable stripe RAID. So by doing that, we've done this thing where if a chip starts going bad, we only take 1/16 of 15 chips out of production. So we're able to expand the lifespan. But that also means typically in other arrays, an SSD drive or whatever, when chips start going bad, you're losing performance because the system has to take an entire chip out of the configuration. We don't need to do that. We can do this at this very tiny incremental level and keep the chips running. Then from an array perspective, as I mentioned, on top of that, that all happens in the modules. But then we take the modules and do this stripe set, RAID 5 stripe, across the modules. So we have 10 data modules and one parity module and one hot spare. So that gives us this ability to have the enterprise class hot swappability, no single point of failure that I mentioned. All of this goes in this box, and I won't spend too much more time here. You know, all of this is just shows the hot swappability, et cetera. And as I mentioned, the size of the units, I'm sorry, it's 1.2 terabytes to 5.7 terabytes in the modules, which, as I said, takes us from, well, smallest unit, 2.2 terabytes, up to 57 terabytes usable in the 2U array. Now, that's where it gets interesting, because as I mentioned a minute ago, when you start thinking about the spinning disk and the fact that people stripe across multiple disks to get performance, that case I mentioned with Penn State where they had 200 spinning disk drives, right? We took those 200 spinning disk drives in 4 cabinets and we replaced them with one of these 2U arrays. So, you know, if you're in a colo or something, the cost of a rack of space, and the people I've spoken to across the country, depending on where you're living, a rack of space in a co-location facility can be $60,000 to $120,000 a year. So if we replace 4 cabinets of space, $200,000 to $400,000 of savings just in the space in a co-location facility. But the other thing that we did there is, in that case, you know, those spinning disks were 60 terabytes of capacity. We replaced that with 10 terabytes of flash because we had this much higher performance, right? And that was actually only 40,000 IOPS they were looking for there. And as I said, this has this headroom that's, I don't even like talking about 1 million IOPS because nobody does 1 million IOPS, but we had this headroom to go ahead and do that. And, you know, we put in a 10 terabyte unit. So we know that 60 terabytes of spinning disk was required and only 10 terabytes of data. And we know it's only 10 terabytes because that's all the flash we used to replace it. And we got all the data into that array. That means they were using the disk arrays at 15% utilization. So that's how we can kind of start having this conversation about how flash is cheaper than disk. If you're buying, you know, 60 terabytes for 10 terabytes of data, that changes the metrics dramatically. Now, I put this in here just as an example, and we'll walk through some more of these in a minute of where to use flash and how to connect it to where it has best benefit with power servers, et cetera, and some of the different applications. But one of the things we saw is a lot of those applications, or the success stories I mentioned earlier, a lot of those were SAP. And one of the reasons that people were moving to SAP HANA, I mean, obviously by 2025, maybe I thought I heard 2026 the other day, people need to move to HANA with SAP. But one of the reasons they were looking at it sooner than later is this performance boost. Well, the cool thing is we put a flash array in today on SAP. We've seen people, like that example I gave of a 10x, 40 hours down to 4 hours on a batch process. That was an SAP application. So we see these tremendous benefits today, but then the nice part is it's not a wasted investment, because even when you move to HANA and it's an in-memory database, you still have the backups, you still have the log files, you still have the case of when you might want to actually, hopefully, occasionally you'll have to start the database up again, in which case you want to move it back into memory as rapidly as possible. So the persistent disk where you keep the HANA database matters here, or the persistent storage, which I would make the case should be this flash array. And the other thing that's going on with HANA, of course, is the dynamic tiering. So, you know, it's possible to look at this as the place to keep the warm data or cold data and still get performance advancements. Now, that's the FS900, which is the goes fastest in the industry, but arguably we have the best storage virtualization engine in the industry as well, with, last time I heard, 12,000 implementations, and I think it's significantly higher than that now, of SVC. So we've got many customers using the FS900 behind SVC, but we also created the V9000 as an appliance based on the FS900, which put the SVC virtualization capabilities, compression, snapshotting, all that stuff The FS900, as the goes fastest in the industry, as I said, is the Indy car. There's no functionality in there other than doing fast IOPS. Well, in enterprise class, you probably want some of these snapshots. If you guys are doing DevOps, this is a great way. Think about being able to create a snapshot instantaneously. And oh, by the way, you can create it on the same array and not have a performance impact on your production version, because we have that million IOPS as that top level. So you can have deb, test, QA, whatever on the same flash storage array. You don't have to move it off to a test array or move data around. You can just use these snapshots and create images very rapidly and get best performance with QoS, if you wish, to make sure that your production version is getting the high performance. So it's a really good story to add it with the SVC and do storage virtualization and get the scalability. You know, we actually had the ability to put these together. If you're going with the V9000, it scales up to this ginormous one in the middle with the 456 usable terabytes. We said 2.2 petabytes because of an effective number when you start doing deduplication and snapshots, compression and snapshots, etc. So lots of IOPS, lots of capability, lots of functionality there with storage virtualization so that you can share this thing and do that DevOps story. And as I mentioned, because we have that high, you know, this is where the million IOPS becomes interesting, even though a single application might only, the highest application I've seen, other than like Google and Amazon and some of those other, you know, the highest real application, business-based application would be, I saw one that was like 125, 150,000 IOPS. Generally, the 50 to 80,000 IOPS is more realistic for most applications. So, you know, you have the headroom in here, as I said, to do other things in this array. So you can do some data center consolidation and get some benefits there from doing this. And as I mentioned in the DevOps story, there's a good case for that. I don't want to go through this very much. You know, I started with IBM 9 years ago, as Joe mentioned. We had the XIV array that we just introduced or acquired and started selling quite a bit. The whole idea there was a grid infrastructure for storage to give fiber channel type performance, right? Tier 1 disk performance with the tier 2, tier 3 type pricing. So by doing this grid and balancing the data and having all this stuff and doing the data distribution so that all the data got spread across all the spinning disks, right? This was all based on spinning disk. And basically what it did is it gave that result of 5 millisecond response time that's normal for a fiber channel array, 2 to 5 millisecond response time for a large workload, lots of threads, lots of applications. By you doing this grid thing, it gave that predictable performance using SATA drives. So the tagline for XIV, which is great, you know, is tier 1 performance and functionality, all the snapshots, all the replication, all that stuff, tier 1 performance and functionality at tier 2, tier 3 type pricing. The beauty of it was the grid infrastructure that came with that thing. So the reason I mention that is because for the people who are familiar with XIV, we created the A9000 as another line here that is based on the XIV grid technology. So now all of a sudden in an A9000, which is, again, the base unit inside there is the FS900, which is our goes fastest flash in the industry. But what happens there then, inside there is we put the XIV grid infrastructure over it, and that gives us compression and deduplication, plus then provisioning, replication, encryption, you know, all the shins, everything you need for a production class environment. And it does that at a 0.5 millisecond response time. So basically, we've created, this thing can replace, as it says there, you know, there's 57 terabytes in there, even figuring 3 to 1. If you go 5 to 1, you're looking at 285 terabytes of effective capacity in 6U at a half millisecond response time. So, you know, we've seen cases where this is absolutely, actually we've seen cases where the FS900 itself was used as a replacement for entire storage arrays. I don't want to mention those 3 letters, EMC, but, you know, in cases we've seen where they just completely took one of these 2U appliances in the FS900, and now we're seeing more cases of this 6U. At 0.5 millisecond response time, you can replace a lot of big iron full cabinet storage arrays with one of these appliances. The A9000R, the rack version, gives us, as you see, up to 1.7 petabyte effective capacity in a single rack. And again, it says those, 3.6 million IOPS, and we're aiming at that 0.5 millisecond response time level. So significantly faster than a lot of the big iron arrays, which are routinely 2 to 5 millisecond and higher, and significantly smaller footprint in the data center with better performance, right? All the software stack, the snapshots, the sync, async replication. I don't need to read all these. You can read these as well as I can. But the point is, it's enterprise class functionality with very, very high performance and reliability. And of course, it has a cool GUI. Well, the nice part about the GUI is it does allow for self-provisioning as well. It allows somebody who manages a bunch of arrays, a very simple set of tools to manage those arrays from a single point, and it goes the other direction where you can allow multi-tenancy and self-provisioning. The reliability is because we use these interface modules. Again, we're using the FS900 as the base unit, and we're using the servers to create that grid infrastructure of, in a pod, we're using the 3 servers to get that level of reliability, and everything's N+1 high availability. In the rack, we just put these together and get the much larger configuration. So we have that ability. It's funny, again, so many people, 57 terabyte usable capacity with a 200 plus effective capacity. I'm selling a lot more pods than I am racks and having people implement those. But if we do go with the rack configuration, it very much does that same thing in terms of spreading the data across, like the XIV technology did. Well, it's kind of the same picture. I won't spend too much time on this. So what did all this mean, right? Here we get to the part. So that's what all the components were, right? And with the FS900 being the base unit of the Goes Fastest IndyCar, we tied it together with our SVC virtualization engine for people who are doing that, the virtualization across different heterogeneous environments. So we come up with the SVC behind in front of FS900s, but also the V9000 appliance. And then with the XIV grid technology, we tied it together and came up with the A9000. And that software stack can actually, we refer to that as Spectrum Accelerate. In the SVC or the XIV scenarios, those tie across the platform so that you can indeed do replication with like units that are still in production or whatever. But then, the gist of this, those are the units that we use. So what does it all mean? And these, I put some examples here of what people have done with it. I forgot, there was a point I wanted to make on this one that I thought was very nice. Optimizing resources while improving performance is what they said. We've got, like I said, there's 272 of these stories. Copy services for core banking. So here again is the idea where they use the A9000, which has 200 terabytes of effective capacity at 0.5 milliseconds. So they were able to create their dev, test, and QA versions incredibly rapidly and still get the highest performance out of all of their versions or copies, doing analytics, doing development, all that DevOps stuff. And it did not impact the performance of the production image. And they did not have to do the sprawl of having different storage for those different implementations or those different versions. So this takes us back. Let me talk, so as I was preparing for this, I went and dug through some of the stuff that we have on the different things that people were doing with Power and with Flash. And I'll tell you what, I came up with a couple decks on SAP HANA. Somebody out there has collected a bunch of data. I found a deck with 385 slides, which, I didn't think you guys would appreciate this morning. They were all on SAP and SAP HANA with Power and with Flash. So there was another deck that had consolidated a little bit. Suffice to say, we could spend this entire time talking about how SAP and SAP HANA work with Power 8, SAP HANA on Power, and how it works with Power 8 and how it works with Flash. Now, we started this, as I said, as the Texas Memory System acquisition when we created the software-defined and flash storage team, which is what I used to be, and Joe pointed out I left on my title here. In the SAP Business Suite, or all the SAP implementations, we showed folks how if you put this flash array in the FS900, at the time it was the 840, but same concept here with all flash array. The 840 was the original version, and now we're up to the FS900 version 4. Went from 20 terabytes to 57 terabytes, etc. But the gist of it is, in this case, what we showed people is for a true business continuance DR scenario, they put it behind SVC so that they could indeed replicate. Now, what's great is all of the reads, the writes have to go to both places in this case, but in SVC's case, they can do the write to the other end and get that performance. All of the reads come from the flash, so you're getting top-notch performance on the SAP application, and you're getting a level of reliability for a classic business continuance DR scenario. But what we saw with SAP, let's see, is this, okay, I went through this one. I apologize. I ended up putting this in 2 places, so we'll just go past this one. I thought I saw this twice, but I missed that when I was doing this. But then the other thing that we did is we saw these cases where people truly wanted the reliability of having 2 copies. So in this scenario with SVC, what we did is we've got the, this was before we kind of did the flash is cheaper than disk. And I'm going to get to that in just a moment and make an argument that you should not be spending any money on spinning disk in a moment. So I'll tell you that in a second. But the gist of this was, look, put a flash system as the primary data and have traditional storage as the secondary. So it was a way of, taking advantage of the current investment and using the current storage for the second copy. But what we did here is all the writes went directly to the SVC unit, so they all got cached, and then the reads all came from the flash. So what happens there is all of your reads end up at 0.2 milliseconds, and your writes, because they're going to the 2 different scenarios, the disk, they're going through the cache, your writes are somewhere around a millisecond response time. Right? So your overall architecture, instead of being 5 milliseconds, your reads are 0.2 milliseconds, your writes are now milliseconds. So your overall improvement as compared to your traditional storage was tremendous, and yet in this scenario, you're able to take advantage of your investment and continue to use your disk. Now, here's the case. I'll show you 2 slides here, and the reason Joe told me, this is not, I'm not trying to sell here. He told me this is not a sales thing. I want to show you this for one reason, and that's really to show you that if this makes sense, and using this technology and getting this performance boost and having this tool in your toolkit, if you will, whatever, it has to be price competitive. It has to be cost effective, right? So what this case showed is we did a scenario a couple years ago where we ran this thing as an example. This was an artificial test, but we said, look, let's create a 43,000 transaction per second scenario for an application. The result to get those 43,000 transactions per second is 1.3 million IOPS, 13,000 updates per second, right? And then we said, okay, what does that cost from, now let's look at $1 per IOP. Instead of the traditional, here's what it costs dollars per gigabyte, what does it cost in dollars per IOP? So you see the result here, dollars per IOP. Flash, the dollar spent on flash storage to get the same performance in a hybrid scenario of flash and SSD, you go to $11. To do it in spinning disk, you're at $14 per IOP, right? So 14x cost to go with spinning disk as opposed to going with the all flash array when you do it on $1 per IOP. And of course, you can see the energy and space savings here as well. It's interesting when I have conversations with data centers, a lot of folks are like, yeah, I don't pay for that stuff. And, that's true. in a lot of scenarios. But the other thing I've found is a lot of companies now, there was a couple that I've gone and looked at their website and looked at their corporate mission. One of the things that companies are putting on their website at this point is this bullet about being green, being concerned with the climate and with the environment. And, you know, Amazon sends us those things about, did we ship it in the right packaging? You know, is it effective? So Amazon actually is one of them who, if you go to their website, they talk very much about being concerned with climate change and being good steward, you know, the right packing material, not too much. So it's an interesting point that you could use this to not only save green dollars, of course, that kind of green, but you can also have the argument that this is a tremendous savings in the data center and, you know, a little feather in your cap in terms of that perspective. But then if you look at it slightly differently, I'll go through this one again, just so you kind of have this idea in your head to show that this is indeed not just pie in the sky, but something that is not only cost effective, but actually a benefit. You know, not only is it going to run faster, but it's going to be cheaper. And I'll just give a couple examples here. One of my favorites from early on when we were doing this, the flash storage, is the 38% software. This is from Wikibon, by the way. But I saw a case where I was working with a customer who was looking at flash versus disk. So we did this benchmark with a guy, and we showed that one CPU, for his application, one CPU attached to flash outperformed 5 CPUs attached to disk. So it wasn't a CPU issue. That thing I showed you earlier, right? The chart where we saw that it was 70% weight IO, and when we changed that to 2% weight IO, the CPU utilization went up dramatically. So that's what this guy saw. And he didn't really buy off on the fact that he could do an 80% reduction in CPUs, but he did buy off on doing about half the number. He actually bought all the CPUs. So I'll tell you guys, you know, when you're doing DevOps and you're doing test and QA, there's a lot of times there's other reasons to use the CPU. So, you know, a lot of times I still see people not making that decision. But what I do see them doing is for the production application in that case, an Oracle database, his street price was like $20K a pop, and he reduced 19 CPU licenses for that implementation. So there was a $380,000 savings just in Oracle licensing. You know, then you have that conversation that we had earlier about, you know, if you're paying for your rack space and you can go from 4 racks down to a 2U appliance, all of a sudden, all these things, right? The higher storage utilization, where I said there were 15% utilization on their spinning disk, and we went to 97% utilization on flash. Fewer servers, you know, that may or may not be true depending on what you're doing. But one of the amazing things that I see is, why do people virtualize? Why did you all go with, you know, Power VM or, you know, those other guys? Why did you all virtualize? The reason is because 80% of the CPU resources that are not virtualized go wasted. So we've all tried to reduce the footprint in the data center, reduce the sprawl. This is a natural extension of that concept because of the higher utilization and the modernization of the data center. And then, of course, you know, less power, less cooling, the less operational support costs, and so forth. And if we can just eliminate that idea of hotspots or data placement, et cetera, it kind of makes it all easier. So look, there's a number of use cases here. There's 2 of them that I want to spend a minute on, and then we'll get to one last thing, and I'll wrap this up. This is a good case as a service provider of a company. This is actually in Europe, but they're an SAP service provider. So again, as a service provider, this gave them that boost in SAP response times. And for them, of course, colo facilities matters. 97% cut in footprint and decrease in power mattered to them from a data center perspective as a service provider. This case study that's out there on the web and is available was very fitting in with what I was talking about earlier. You know, it says all the usual blah, 97% reduction in processing time, 20x more data crunch. But here's the deal. This is Coke distribution. They load up their trucks every morning at 5 a.m., whatever it is, right? Every 24 hours, they're loading their trucks. Their batch process was running more than 24 hours. So this takes your application performance into the real world. If I'm loading a truck and I don't have the information about yesterday, how do I know what I'm putting on that truck is right? And here's a case, right? If I go to Amazon today and I can't get the performance I want, I'm probably going to go back later because I do a bunch of stuff on that website. But if I walk into 7-Eleven today and my can of Coca-Cola isn't there, I'm not going to go back tomorrow and buy 2 cans, right? So they figured this out, that this is real dollars in the real world by having the wrong product, not having the right product on the shelf, but also costly as shipping product that people aren't buying. So we put this in, and all of a sudden their batch window went down to about 4 hours. Well, now if it's 4 hours, now they can look not only at yesterday's data, they can look at what are we on, Thursday? They can look at last Thursday's data. They can look at a month ago on Thursday. They can look a year ago, the same date. So now all of a sudden they can do this extra work that adds better business value in the real world for these guys. So I love that case about doing that kind of thing. Mentioning no names here, this was absolutely a case where we started with a single unit and showed the tremendous benefit in the analytics thing. And these guys, you know, the real answer of how these guys make money is through the contractors. So they did this thing with Splunk to figure out how to give better analytics and do cooler things with their contractors, et cetera. So this had a real business benefit as well. But the fun part about this, he sees that 90x faster than EMC VMAX. This absolutely became a case where somebody in the case asked the question, well, why don't we just replace all that VMAX? You know, basically, and they're actually looking at becoming an all-flash data center, no more spinning disk in that data center. There's some other examples here. This is a great one in terms of an Oracle database, and that's where we saw a lot of benefit. You see it's with the Power Server as well. You know, going from 6,000 to 50,000 users and still getting better performance out of it, that's a pretty good story if you can add additional workload and not have to worry about balancing to get the right performance. There's a bunch more examples in here. I mean, the healthcare one I think is a great one that we've seen in a number of different cases. You know, when we start thinking about everything that physicians and nurses and everybody has to do in the healthcare world in this day and age, and how they're all being crushed by the paperwork instead of the customer time, it's a different measurement when you can provide faster response time at the workstation. And of course, hospitals are all measuring this by what they call outcomes. So this also means you can have better data analysis and better information when you are working with the patient, which typically also results in a better outcome, which is what they're all measuring. So, you know, there's absolutely scads of these examples. If you get to the last page in this, I'm not going to go through all of the examples that I put in this presentation. There's so many of these different success stories. As I mentioned, somewhere around 300 of them. But I did include a lot of these examples at the end of the presentation, including one with the, where'd I go? Okay, sorry about that. Including some that had to do with, I'm sorry, there's some links out there with some public case studies that you can go look at in your spare time there. But the last thing I'll mention here, and then we'll see if there's any time left for questions here. The last thing I wanted to mention is one of the things we did a while back is created this thing called the CAPI interface. CAPI basically gave us, it's using the NVMe concept there, using NVMe connectivity to give us the performance of almost in-memory performance while using flash storage. So CAPI was designed, it's an interface that you can write to. So at this point, there's a handful of different vendors, Redis. There's 2 others that I know of that have written to the CAPI interface. But there's 2 different cards that are available on the Power Server. One that actually has a little bit of flash on it, I think 8 gig. I don't know. It's a fairly small amount of flash on it. But then the other thing that CAPI gives us is a card that goes through the PCIe bus and gives us that connectivity. You know, obviously on the server side, it's connecting the GPUs, et cetera. But we also have the connectivity to the exterior flash array. So we can use CAPI to connect to the FS900. And then what you end up seeing there is this idea, what CAPI tried to do is reduce the instruction set. So you're eliminating the traditional stack of doing I/O, and you're effectively going straight to the flash storage. So you're getting the performance of flash instead of slowing it down through the traditional fiber channel SCSI instruction set. We have CAPI running. It's running, there's 3 different things that have written to it. The Redis database, there's, I can't think of the other one, but there's a couple other databases that have used the CAPI interface. And there's a gzip, there's a handful of things that have used the CAPI interface. And as we move forward, of course, this is based on the NVMe standard. So we will be looking at total, standard NVMe support as well. Nice way of thinking as well, as we mentioned with SAP HANA earlier, if you have the dynamic tiering and you're trying to figure out where storage can be kept, it's a really interesting idea of having hot data, warm data, and cold data, and yet the cold data is available through NVMe and cache. It gets this kind of performance boost, right? You look at what it does from a traditional I/O perspective versus a CAPI perspective, much lower latency number, much higher throughput capability. So look, that's, I want to make sure, as I said, there's 2 things I wanted you to walk away with here. One is the fact that we have this application acceleration capability. And the other is that it's something that is truly effective in the data center and is cost effective. So now we can actually think about things like replacing spinning disk and becoming an all flash data center. And it is helping, not only is it flash cheaper than disk, but, oh, hey, by the way, you run considerably faster than you did on that spinning disk. So to that point, the thing that I would offer, if this makes sense and there's something you want to follow up on or something you heard here, obviously I'm available. Joe can connect with me. We have other people on the storage team you can connect with if there's things we want to look at. I would offer 2 things that you could follow up on. One is the AWR report. As I said, we can run that AWR report very simply, any Oracle database. We can show you what it would mean to add this to Flash. I was meeting with a customer recently I was at an executive briefing where I was presenting Flash, and these guys were doing life sciences, right? They were looking at how can we look at what this single molecule does to within somebody specifically, right? So all this targeted medicine and stuff, but they needed this this high performance analytics, and they moved from x86 to Power 8, and they got it to where the processes are running on, cores that are side by side. They got the thing to run dramatically faster by moving to Power. And it was working on like a 200 terabyte working data set. We're like, look, you connect the Flash and now you get that extra boost from when you're loading it and when you're saving your results. So all of that stuff we can, with an Oracle database or even others, DB2 if you wish, but Oracle has the very simple AWR report. Give me an AWR report and we can turn around a response as to what this would do to your specific application. And then piece 2 of that I'd offer is one of the other things that we're seeing is we have a study, something that's come up a number of places recently in conversations I've been having in Hadoop data sets is obviously Hadoop has that CPU to storage ratio. If we could change that, and we could have a scenario where you understand what data is hot and what data is cold, and you could place data up accordingly, then there's some benefits to data placement and fewer CPUs or growing storage, kind of breaking that tie so that you can more effectively size the implementation and potentially save on the cost of storage, potentially servers, and probably software licensing for that kind of scenario. So we have a study that we can offer for that as well. So if either one of those studies sounds interesting, I'd be happy to follow up on those. So that's what I wanted to present this morning. As I said, it's been phenomenal working with power users who have started implementing this and have seen these results. So that's why I wanted to make sure, you know, when Joe mentioned this to me, I got pretty excited about having this conversation and sharing this with you. So thanks for your time there, and I will open it up to questions.
All right, fantastic. I'll tell everybody, Jeff mentioned this topic to me. At first I was pretty skeptical because, you know, it's a storage topic and I'm all about power systems, but actually they do marry together very well, and I really appreciate Jeff coming on and pitching this. There's several questions out there, Jeff. Let's start kind of at the top with some other flash vendors. And can you make any comparison to like how the flash that you talked about here compares to, say, EMC VMAX, which is pretty well known out there?
Sure, happy to. And I kind of dropped some hints throughout, right? Every one of the other vendors that is doing this, that is in existence today, is doing this based on SSD drives that are emulating a disk that sit behind disk controllers. And oh, by the way, the minute that you put them in behind a disk controller with a disk, even a 15K RPM disk drive, you know, one of the customers that I went to was looking at exactly that concept, said, look, the minute I put SSD drives in there, it all falls down to the performance of the fiber channel drive. So a lot of times what you're seeing is you're putting SSD drives with high IOPS capability and, you know, 1 millisecond response time behind a traditional controller that can't do near that response time or near that performance. So it actually becomes a case of having a really big infrastructure. God, I wish I need a good analogy for this, but you know, you're, I don't know, putting a Ferrari engine in a dump truck, you know, something really silly. So as I mentioned a number of times and dropped hints, everybody else is doing this based on SSD drives, and their performance, actually somebody told me the VMAX, okay, I won't say names and I won't give the exact number, but suffice to say that the VMAX with SSD drives is not aiming at a 0.2 millisecond or a 0.5 millisecond response time. They're aiming at somewhere around a 5 millisecond response time. So now what you've just done is paid a bunch of money for flash storage that's performing at similar to fiber channel drives. Now I will say that's the published stuff that I've heard and seen talked about. People have done better, but traditionally those arrays are going to get 1 to 2 millisecond response time with SSD drives, as opposed to the 0.2 to 0.5 millisecond response time we get with the all-flash array because of that design from the ground up. Okay. Same with Pure, you know, all the other guys are indeed based on SSD drives. Pure, Extreme IO, all of them.
Yeah. Well, how hard would it be then to migrate from a VMAX to Flash to an IBM Flash?
That's a great question. I mean, there's a couple of different things that we can offer from that perspective. A very simple way, as I mentioned, the guys that did the POC who put it up and had it moved in 3 hours, they just connected, you know, the flash array does indeed appear as disk drives. So they assigned some ones to a host and used the LVM to move the data, and they were up and running 3 hours later. We do also, of course, have the option of using a V9000 or an SVC array, or SVC appliance. We can put that in front of the EMC and migrate the data using the SVC functionality, basically transparently, right? So you can, once you take an outage to put in the SVC, and then we can migrate the data using the SVC from an EMC to a flash array. We have a number of people who've done that. You know, the SVC, as I said, arguably the best virtualization engine in the industry. We have many customers who are running SVC in front of EMC, Hitachi, and our own storage, of course. So either way, it's pretty straightforward.
So several people mentioned, you had talked about all the slides you have for SAP HANA and that, and several people wrote comments asking for those slides. So I'll just throw out here, if you want the slides, more slides. I mean, this deck that Jeff has gone over is on the AIX VUG wiki. If you want these other slides that Jeff talked about as well for something that you're doing, send a note to Jeff or myself, and we'll get it from there. Send us an email, and then we'll try and get you what we can from that. Okay. Actually, If you send it to me, I'm going to forward it to Jeff because he's going to handle all of that.
Fair enough.
All right. Let's see. Next question maybe. There was a question on the dedupe functionality. The question was, is it coming to the V9000 or is it just on the A9000? Because it wasn't actually in the slide, they said.
TBD, it is not on the slide because I don't know. I believe the conversation is occurring. I don't believe that we have committed to a date at this point. So at this point, compression and deduplication are in the A9000 and compression only in the V9000 SVC functions. But it is in consideration. I don't think we've committed to a date.
There was some kind of question about comparison to the Hitachi as well. I'm just going to let that go as, you know, it's the same as what you mentioned kind of generally about comparison to all, you know, EMC, but I think the same holds true to Hitachi.
Agreed.
Several people wrote in about the SVC, and, you know, you showed a nice picture with that kind of in between the flash and the system. Is there, can you expand a little bit on the benefits of that? You know, I'd sent back about, we could do a whole session on SVC, and somebody said that would be nice, but maybe if you can just talk a little bit about the SVC in general, Jeff, and whatever performance improvements you get from having the SVC there as well as the other stuff.
Sure, and generally, the SVC is not a performance boosting tool, right? We put it, the FS, okay, so let's look at it from two perspectives. On the FS900, that is our goes fastest in the industry. So definitely, you know, in those cases where we've replaced 200 spinning disks, and other cases where we're replacing a VMAX, the FS900 being all flash array is the goes fastest Indy car. And you can make a case that it is indeed cost effective in a lot of those instances. But to get to that next level, SVC is what gives us the functionality, right? That puts the back seat and the trunk and the baby seat in the Indy car and the air conditioning and the, you know, CD player. So that gives us all the functionality of the thin provisioning, the snapshots, the replication, the data movement and migration. So as I mentioned, what a lot of people use SVC for, they get two major benefits from SVC, whether it's in front of our storage or in front of other people's storage. Sprint was a case study we did years ago where they put SVC in front of a lot of EMC and they were moving, you know, fortunately they were moving to a lot of our flash stuff as well, but they put it in front of all their storage, and basically they said they went from like a 30% utilization level on their spinning disk to a 70% utilization on their spinning disk. So SVC is a great virtualization tool for storage that gives you that functionality of snapshots, replication, thin provisioning, compression, etc., and generally is used to virtualize the storage and get better performance or better utilization as well as the functionality. We use it in the V9000 because we have many customers who don't want just the application acceleration and they're not going to change their whole environment to SVC, but we can deliver the V9000 as an appliance that gives you, you know, 0.5 millisecond response time instead of 0.2 millisecond response time, and it has all the functionality. So if you're going to look at, you know, virtualizing your entire environment or a good chunk of it to get better utilization and or the ability to move data from one array to another transparently, SVC is a phenomenal way to go. If you're just looking for a virtual appliance that's based on flash and gives you tremendous performance with enterprise class reliability, that would be the V9000. And of course, the A9000 is taking us another step in the Spectrum Accelerate software side with the compression and deduplication.
All right. Jeff, can you talk a little bit about monitoring capabilities with Flash? You know, how to tell what your, if it's different, if there's specific tools to use for monitoring if you have Flash systems on?
Good question. I mean, obviously the A9000 has monitoring tools built into the GUI. You know, one of the things that XIV had when it came out into the marketplace was the easy button, right? The comment we had at the time was, Okay, I won't tell you the jokes we made, but suffice to say that the GUI was so simple. There was one guy that I worked with, there was the storage admin, and he's all like, we're not using that GUI, we're command line. And I walked in 6 months later and he was doing everything on the GUI, and he looked at me a little sheepishly and said, yeah, it's too easy. I don't need that command line stuff anymore. So all that, the easy button is built into the A9000 from the Accelerate side. On the V9000 side, SVC, Spectrum Virtualize has the Spectrum control functionality, and in that case, the flash just is managed the way you would any other persistent storage. So that has all the tie-ins and has all the management capability and all the monitoring capability. The FS900, then, if we go back to that level, which a lot of people do for the specific application that needs screaming performance. And oh, by the way, it gets deterministic screaming performance, right? It doesn't change based on what other things are going on. It gets that 0.2 millisecond end of story. So a lot of people use that for a specific application that needs screaming performance. That gizmo is absolutely more primitive, but it has all the messages that you could put through a monitoring tool and keep track of it.
All right. Since we're talking about management, there was a question about Spectrum. Does it manage the flash storage the same as other storage?
Yes.
It does. Okay. I'm just kind of going through here and trying to see which of these we didn't really talk about yet. You mentioned Cappy. Jeff, there's actually a couple of these that I think you mentioned already. One is the redundancy for Flash, and I know you had some charts on that, but there's still a question on it. So before we get to Cappy, because I think probably the redundancy is much more meaningful here than Cappy. Can you just go back and just talk a little bit about the redundancy that's built into the Flash and why it's not a single point of failure and an enterprise?
Absolutely, because I did kind of go over that quickly, and thank you for the question. It's unique in the industry, and I'll tell you why. It absolutely, I can spend we need a whiteboard, but think about it this way. First of all, let's remember there's 12 modules. Right, so let's do the high level first. There's 12 modules in a Flash FS900, which is the base of everything I've talked about today, right? So in the FS900, there's the 12 modules, and the modules are protected in a striped array with 10 data modules, 1 parity module, and 1 hot spare. So from a module replacement perspective, it is, with a hot spare, it is hot swappable. So there's no single point of failure there from the viewpoint of replacing any component in the array, including the modules. Then what we do is we go a step further to give you a level of lifespan and reliability that's unique in the industry. So first of all, if you do the math on that, with the 5.7 terabytes, everything that I've said about the capacity and the usable capacity is based on what, we charge based on that. But in reality, 57 terabytes, that's your 10 modules. We've got the hot spare and the parity module. I didn't include those when I say 57 terabytes. So there's actually something, I forget the exact number, somewhere north of 100 terabytes of flash capacity in this array, which means there's somewhere like 30% additional capacity on each module. So that gives us some really cool things that we can do. The first thing we can do is, that means if if you're familiar with the way Flash works, when you write to Flash, it has to go through an erase cycle before you can write to it again. So that's one of the things that people see, is that write amplification problem from a performance perspective. If you're writing too fast, then you overrun the system. It has to go through that erasure stuff before you can actually write again. We've avoided all of that. We do not have a write amplification issue because of that extra 30% of capacity, coupled with the fact that we're basically, spreading the data across all the chips in the array kind of thing and treating the chips as a grid. But at the module level then, we actually have the chips broken up into 6 sets. And on the module, to keep to do everything we can to not have to replace a module, in the sets, as I was talking about, we have this variable stripe RAID thing. So in the 6 sets on the module, there's 15 chips per set. And each chip, this is topology of chips that everybody uses. There's 16 pages per chip. So basically we have 16, in each set of 15 chips, there's 16 different 14+1 stripe sets at the page level. That's how we get that really, really granular protection, as well as the fact that if we have one cell fail, we only have to take 1/16 of a chip out of production, and then that stripe set goes to 13+1. But we move that, we have that other 30% to use where we can repoint to another cell somewhere or another page, so we don't actually lose capacity, usable capacity at all. And we can take a lot of page hits before we actually have to replace the module. So that variable stripe RAID set is unique in the industry in terms of keeping chips available for performance, as well as expanding the lifespan so that we can provide that 7-year guarantee. Unique variable stripe RAID, and then the 2D RAID on the modules themselves to give us that reliability and redundancy. How's that?
That's great. So there's another question here, and I think I already know the answer to it, but I'm just going to let you talk about it anyway. And this is, you know, we came out recently with the read-intensive flash drives. All right, so we're calling them flash drives, and they're read-intensive, and they're better performance. So the question is this the same thing as a flash array? And if it's not, you know, can you explain a little bit of the differences?
Honestly, I cannot explain the differences this morning. I have not spent that much time. It is not the same. I honestly have not spent enough time to be able to give a cogent explanation of the differences. I suspect it has to do with a bunch of DRAM in the front of an SSD drive, but I'd have to look at it further. So I can take that one and post a response to it when I can get a chance to research it a bit, but I can't answer that one right now.
Okay. Is there so the next one here is a distance for the flash array from the server. If there's how the distance is affects the performance, what the distances are allowed for that?
So think of it this way, the FS900 or either of the other arrays think of them as if they were traditional storage arrays, fiber channel storage arrays. So today for the FS900, we have either fiber channel or InfiniBand interconnectivity. But let's step back one step. When you attach the FS900 to a SAN, then you have a GUI that allows you to take that 57 terabytes and slice it up into LUNs. At that point, those LUNs look just like a disk to your power server, right? Or Linux, you know, Linux on power. So, but the point is, they look like a traditional disk drive. I do all my magic in the back end without disk emulation, right? I spread those LUNs. If you create a 2 terabyte LUN, it actually gets spread across all the chips in the array. So that's how I get screaming performance of 0.1 millisecond at the front when chips themselves don't run at 1.1 millisecond. I avoid all the disk emulation in the back end. The front end, of course, I emulate disk drives. So you see a 2 terabyte disk drive at your host, it just runs super fast. So to that end, and answer the distance question, the distance is traditional fiber channel storage array. We have traditional fiber channel HBAs in the array, and of course in your SAN. So I forget the exact numbers, but traditional storage array of, I think it's 30 meters, but I don't remember at this point what classic fiber channel distance is in the data center.
All right.
Well, I'm sorry, one other answer. No effect on performance for distance because it is fiber channel, it's optics.
Okay. This one, I'm not really sure. I'll just read you the question because I'm not really sure what the SRDF. It's what technology do you have to replace SRDF for replications to another site?
Great. That would be SVC, in the V9000 or in the SVC, we have the Metro and Global Mirror functionality available in SVC. And the A9000 itself actually comes with its own replication technology, which is indeed proprietary to the Spectrum Accelerate family. So, you know, today we can do replication between one A9000 and another A9000. As we grow, you know, there's another release coming out where we can do replication between an A9000 and the traditional XIV storage arrays. So it's kind of a this or that answer. If you're going with we have people who are dedicated to the XIVs and to the what we now call the Spectrum Accelerate software. So an A9000 works great, and that has all the replication built in. Otherwise, we're going to go to the SVC functionality, which can go in front of any storage array, including the FS900, and provide that replication capability.
All right. So this next question is a little bit specific to the competition, and there's a VMAX 250F all flash VMAX, it says, and so the question is that still use SSDs?
Yes. Yes.
Okay, and sort of a follow-on to that then is, which IBM array would be compatible to that? What would you use to replace or comparable to that or replace that?
Well, you know, based on what we just said, I'd look at an A9000. So seriously, I mean, the A9000 we are using in a lot. So, okay, let me back up a second. So I've been doing this all predicated on power. So my answer that I'm giving you right now is predicated on power servers. The mainframe would be a different answer. So hopefully somebody who's asking this we are talking mainframe. I'm sorry, power. So with power, I would absolutely look at the A9000 as a competitive offering to any of the EMC products, because it gives the same or better reliability. It gives a better price point when you look at the compression deduplication value, and it gives a tremendous performance boost over any of their arrays, even the Extreme IO.
Mm-hmm. And I think we have time for one more question, Jeff. And this has to do with, you know, you talk about great performance, and this question is, will we be able to achieve the performance levels you mentioned using standard native MPIO drivers on AIX?
Yes. Yes, it's all about the speed of what's happening in the flash array. And, you know, I would be happy to, as I said, you know, with the database, I mentioned Oracle, it's AWR, DB2 as I think it's NMON. We have options, but if you have a specific case that you want a specific answer to, I'd be happy to take that and have my team provide a response.
Okay, so I'm going to quit on the questions that are on there. I'm going to throw one last thing out at you then before we wrap up, Jeff, and that's if somebody really wants to do a comparison here, and you know they have a system and they want to try Flash or something like that, what's their options for like a POC or a POT from your team?
We can do a POC. I mean, the thing that I want to do in any case where we do a POC, I would offer that paper POC first that I just mentioned of running the AWR or the NMON or getting some other information. There are cases, I mean, if you have an application that's 97% CPU utilization, I'm not going to help. I might still be able to show you a value proposition of why you want to go with Flash as opposed to spinning disk in the data center. I can probably do that. But if we, you know, depending on which way you're asking the question, if the question is a POC to prove out the application acceleration that I've spent the majority of the time talking about this morning, as opposed to the case of data center modernization and saving money in the data center, then I would want to do the paper study first and get a real guesstimate of what we could expect. I mentioned in the ABB case that I left in the example, we looked at it and expected about a 200% increase, and we saw over a 400% increase on the data center. So this study does tend to sandbag, but, you know, that keeps you from getting mad at me when, you know, because I underachieve as opposed to saying, hey, not too shabby, you overachieved. But I would want to do we can do a POC. We have equipment available. The one thing that I would ask if we go into a POC, let's do the paper. Okay, two things. The paper thing I mentioned already. Let's do the paper analysis first. Secondly, I would ask that we're not just doing a shootout of, hey, let me try a whole bunch of benchmarks. I would ask that we have a specific application that can add benefit or prove that in your shop, this is something that adds value to your data center.
Exactly, because that's the whole point anyway.
Yeah, I don't want to waste either of our time. I want it to be something that's actually going to be useful to you.
Right. Okay, so we are out of time now, Jeff. Thank you so much. This has been fantastic. A lot of good questions, a lot of good material, and I really appreciate you. You know, when we're sitting there talking, and I said, okay, great topic, I guess. So who are you gonna have do it? And you raised your hand. I was like, oh, okay. You did a fantastic job. I really appreciate it, and I'm sure everybody else does too. So thank you so much, Jeff. And
Thanks,
everybody, thanks for attending. And I'll get out next month's invite pretty soon. And I appreciate you all being here. And everybody have a good month and a good summer. So long.